Hi, welcome back to es346 Basic Thermodynamics. This is Module 3.7, Air-Water Mixtures. The sections in the textbook are the special topics at the end of Chapter 3. Here are the two learning outcomes from this module. At the end, you will know how percent humidity is defined, and you will be able to calculate the equilibrium temperature with an air-water mixture. So first, let's talk basically what it means to have an air-water mixture. So here in this picture, we have a lake, and it's in equilibrium with air above it. And air will hold some amount of water in it. And so how much water it holds is going to be a small fraction of the total number of molecules. So recall Dalton's law. Dalton's law of partial pressures that says the total pressure is equal to the summation of all the partial pressures. So if I look at the air-water mixture up above here, I've got two different constituents. I have air and I have water. So I can say the total pressure is equal to the pressure of the water vapor, I'll call it P sub V, plus the partial pressure of the air, I'll call that P sub A. So that total pressure might be the atmospheric pressure, PATM, which is often about 101 kilopascals. Now, in order to find out what the vapor pressure is, the amount of water I have, if I'm in equilibrium, so if the air is at 25 and the lake is also at, say, 25 degrees Celsius, there's going to be a partial pressure of water above it, P sub V, that's equal to P sat at that temperature. So if I go to the saturation tables and I look at 25 degrees Celsius, here's 25 degrees Celsius, I see the saturation pressure is about 3.17 kilopascals. That means that P sub V is 3.17 kilopascals, or about 3% of the total pressure. Now this is at 100% humidity. You often hear humidity reported in percent, which is simply what percentage of P sub V, or really what percentage of P sat, is in there. So in that case, I would have PV is equal to 5 times P sat, where 5 is the percent humidity, 10% or 0.1. So let's go ahead and do an example. So we have an air-water mixture, like atmospheric air. It's at 70 degrees and a relative humidity of 50%. This is usually called relative humidity. And the question asks at what temperature will dew appear. This is a common problem you would see in the morning. You wake up, it's cooler outside, and there may be dew that collects on the grass. That happens because as the temperature dropped, at some point the air could no longer hold enough water and it began to condense out onto the grass. So let's go ahead and calculate what this is. So let's find out at the conditions here what the partial pressure of water vapor is. So PV is equal to 5 times P sat, so 0.5 is my relative humidity, and then I'm going to look up P sat at a temperature of 70 degrees Fahrenheit. So I do that on the table in the back of the book, and that is 0.363 psia. We're looking in English units here, or 0.182 psia. Now, in order to determine the temperature which dew will appear when the relative humidity is equal to 100%, or 1.0. So at that point, PV is equal to P sat, which is equal to 0.182 psia. So I need to go to the table and look at where this value, 0.182, is P sat. Now, if I go to the table, I'll find out that at 50 degrees, it's 0.178. If I look down at the next line, at 55 degrees, it is 0.214. I'm somewhere in between, so I need to go ahead and interpolate. So let's do an interpolation. T minus 50, 55 minus 50 is 0.182, the actual value of pressure, minus 0.178. 0.214 minus 0.178. So I'm doing a linear interpolation, and now I'm going to solve for that value of T. I find out that T is equal to 50.6 degrees Fahrenheit.